Good day everyone. We are Group 8 and today we'll be presenting our work for Activity 8, Guess the Distribution Classifying Random Data Sets. This activity is part of the simulation and modeling that help us to understand the behavior of random events while statistics allow us to analyze data to identify patterns and make informed decisions. Scholastic process ties these together by describing systems that evolve with randomness over time. Our assigned problem involved analyzing multiple pre-generated datasets, each with its own statistical behavior. The goal was to determine which type of probability distribution, such as normal, binomial, or Poisson, and etc. To solve this, we studied each dataset using graphical and numerical summaries. We applied our knowledge of distribution properties to classify the data accordingly. In our presentation, we will walk you through the problem, our solution strategy, a flowchart, and the pseudocode we use for the classification process. Finally, we'll be demonstrating our simulation with at least 3 sample runs or more to show how our approach worked in practice. We hope this gives you a clear overview of our activity, so let's begin.
So this simulation is designed to help determine the most likely probability distribution that fits a given dataset. So it evaluates multiple common distributions such as normal, binomial, Poisson, exponential, and uniform, and ranks them using statistical tests like a Kolmogorov-Smirnov and chi-squared test. So in this case, to run the model, we have the libraries and tools. We use tools like NumPy, SciPy, Matplotlib, and Seaborn to handle numbers and create graphs. And we also use a special tool to help compare our data to common patterns called QQ plotting. Next, we have these candidate distributions. So we choose five common distributions to compare normal, binomial, Poisson, exponential, and uniform. Then we also have this input interface. It accepts the user input as a comma-separated list of numerical values. So it converts it into a NumPy array for processing and handles exceptions for invalid input. And lastly, we have this evaluation function in our source code. A function, evaluate distribution fit, is created and it uses a Kolmogorov-Smirnov or KS test for continuous distributions and uses chi-square test for discrete distributions. And we also skip discrete distributions if input values are non-integer. So before the simulation can run, the system needs to be prepared. So the setup includes importing necessary tools, so defining which distribution to test, and building a way to handle input. So these components that we discuss ensures that the simulation works smoothly and accurately. So once everything is set up, using the simulation is straightforward, of course. So here's the step-by-step process that happens when you enter your data. So first we have this user input. So the user enters the data points as a comma-separated list. Next is distribution fitting. So the code fits each candidate distribution to the data using statistical fitting functions. And the third one is the goodness of fit evaluation. So each distribution is evaluated using p-values from goodness of fit test. Next is the best fit selection. So the distribution with the highest p-value is selected as the best fit. And lastly, we have this visualization or including also the summary or the general summary. Four graphs are generated to help visually inspect the distribution fit and also a terminal summary showing the p-values for each distribution fitting.
Good day everyone, I am Lorraine Alagano. So I will walk you through our flowchart for classifying random datasets. So this outlines how we can take any list of numbers and figure out what kind of probability distribution best fits it. So whether it follows a normal, binomial, Poisson, exponential, or uniform distribution. So first, let's start from the very beginning. So we will start with the user inputting their data. So the user can put anything numerical, and once they have entered the numerical data, that string of values is passed to the next step, which is to parse the input. So basically, in this part, um, we will convert the text into a float array, transforming everything into numbers where the program can actually work with. But we can't move forward just yet because we have to validate the input first. So if the data includes letters, symbols, or anything that can be interpreted as a number, we immediately stop and give a clear message. Invalid input, please enter numeric value separated by commas. Then the program exits. But once the data is valid, there's where the real analysis begins. The next step is defining our candidate distribution. These are the statistical models we're going to test against the user's data. So we have normal, binomial, Poisson, uniform, and exponential distribution. So think of this as our suspects in the mystery of guessing what is the what is the data. So we will going to find out which one is the most likely to match the data, the numerical data that the user have input. So next, we evaluate each distribution. So for every one of them, we run test to calculate a p-value. So that p-value po, it tells how well that distribution fits the data. So after calculating all the p-values, we will sort them from highest to lowest because the higher the p-value, the better fit. Once that is done, we will select the distribution with the highest p-value, and that becomes our best guess. So our best guess will be the most likely distribution type for the particular data set that the user provided. So after we have figured that out, we will move to the output. So the output, we will print the summary statistics like mean, standard deviation, and the skewness. We will also show the p-values for all the tested distributions so the users can compare and of course highlight the best fitting one. But we don't stop there. We also visualize the results. We generate several plots to make the analysis clearer. So we have a histogram with a KDE curve to show the data's shape, a PDF or PMF overlay for comparison, a box plot with a summary of the data, and even a Q-Q plot to show how the data compares to a theoretical distribution. So once everything has been displayed and interpreted, there comes the program will end. So in short, we will take the user's input, clean and analyze it, then test it against the possible distributions, and then finally present both numerical and visual results to help the users to understand their data better. Thank you.
Now we're going to walk through the logic behind the system using the pseudocode. So each part represents a critical step of the data evaluation process from taking input to visualization. First, the system starts to ask the user to enter a system of numeric values. Then, it starts to convert the input into a numerical array. If there is an issue like a non-numerical entry, the program alerts the user and exits to avoid invalid analysis. Next, we define the distribution test. These are common statistical distributions: normal, binomial, Poisson, exponential, and uniform. Each one has its own characteristics, and we will assess which fits best. Next, we loop through each candidate. For discrete distributions like binomial and Poisson, we first check if the data values are integers. If so, we're gonna calculate observed and expected frequencies and run a chi-square test. For continuous distribution, we fit the parameters and use the KS test to compute the p-value. So once we get to the p-values for all distributions, we sort them in ascending order. The distribution with the highest p-value is selected as the best match, since higher p-value means the data is more likely to follow that distribution. We then print a summary including the basic statistics like mean, standard deviation, and skewness. Each distribution's p-value is shown along with the system's best guess for the most suitable distribution. And finally, we generate four types of plots: a histogram with KDE to visualize the data, the PDF of the best fitting distribution, a box plot to show data spread and outliers, and a QQ plot to visually assess normality. So these visualizations help to confirm the statistical result.
Alright, so for the simulation execution, we have here a types of statistical distribution classifier program created by me and John Wilson. How it works is pretty simple. It takes a pre-generated sample data as an input and outputs a graph, mean, standard deviation, skewness, and guesses what kind of distribution it is based on the highest p-value it gets from all types. So what does it mean? So here we have a pre-generated sample data that I've already noted on what kind of types of distribution it is. So let's say I want to test out this uniform distribution. So if you try to run the program and paste the sample data, we can see that we got a graph containing histogram with KDE, PDF, PMF curve, box plot, and QQ plot. At the same time, it also guesses what kind of distribution is best fit for this sample data, and it also displays the mean, standard deviation, and skewness, and tested all the p-value on all types of distribution. Which uniform seems to look the highest, it has a value p of 0.9935. And let's try it again from other sample data. So I want to try this one next, which is the exponential. And if we run the program again and paste it, we can see that we got a different outputs again this time, since the curve here looks different from the previous sample data that we've inputted. And lastly, I want to try the normal distribution this time and try to run the program, paste the sample data. Alright, so this time we got a different result, and we can know that this sample data is a normal distribution since the result here in the graph shows a bell-shaped curve as you can see here, and it also guesses that the sample data that we have input is a normal distribution. And now we have John Wilson to explain this graph in more details.
So after the simulation processes your data, it generates four graphs. So each graphs help us to visualize how well your data matches common probability distributions, and this visuals gives more insight beyond just the statistical numbers, of course. So based on the simulation execution, let us now explain the purpose and importance of each graph result, and finally the outcome showing which distribution fits the data. So first, with the histogram with KDE, it shows the overall shape of your dataset using histogram and overlays a kernel density estimation, a curve for smooth visualization. And the importance is it helps us identify if the data is symmetric like normal, skewed like exponential, or uniform. And it's also good for spotting multimodal behavior or the outliers. Next, we have this PDF or PMF curve overlay. So the purpose of this, it plots the probability density function or the PDF or probability mass function or the PMF of the best fit distribution over your data. So the importance of this is allows you to compare visually how well the chosen distribution's theoretical curve aligns with your real data. So if the curve overlays well with the histogram or KDE, the model is likely a good fit. Then the third one, we have this box plot with stat summary. So it displays the distribution of the data using quartiles, whiskers, and the outliers. So the purpose or the importance of this, it shows the central tendency, the mean or the median, and the spread or the IQR. And it is useful to understand the skewness and whether the data has a heavy tails or outliers. Statistics like Q1, Q3, mean, max, and standard deviation are also annotated in the graph. Then lastly, we have the QQ plan. It compares your data's quantiles against those of the theoretical normal distribution. If the data fits a normal distribution, the points will lie on the diagonal line. And it also helps to identify the deviations from normality for the fat tails, skewness, and etc. So even if the best fit isn't normal, so this plot helps validate or reject normality as candidate. So together, these four graphs help us visually and statistically check with common pattern and best describes the data. So making us it easier for us to choose the right model or assumption for the analysis. And finally, the simulation compares all the five candidate distribution displaying on the terminal output. It shows their p-values, where a value closer to 1 means a better fit, and a closer to 0 means poor alignment or poor fit. So the distribution with the highest valid p-value is highlighted as the most likely match for your data. So in this case, the normal distribution has the highest p-value of 0.9940, meaning it is most likely the pattern that the data follows on the execution of the simulation. So based on the comparison, the best data fits is a normal distribution. And that concludes the simulation execution, and thank you for your attention.
Good day everyone, and I will be discussing the simulation result under the normal distribution. The graphical indicators that the histogram with KDE bell shape closely matches the normal curve. The PDF curve matches KDE well, indicating Gaussian behavior. The box plot symmetrical and centered median with no outliers. The QQ plot points align closely to reference line with slight tail deviation. The data is approximately normal, suitable for statistical method assuming normality. Next, we have the binomial. The graphical indicators that the histogram with KDE discrete and symmetric around at the center, KDE loosely fit. The PMF curve closely matches data frequencies, good model fit. The box plot is symmetric, IQR, one mild outlier. The QQ plot, acceptable deviation due to discreteness, approximate normality observed. The conclusion, data likely from a binomial process, normal approximation may be valid. Next, the Poisson distribution. The histogram with KDE right skewed with peak around lambda 3. The PMF curve matches data well, peak aligned with histogram. The box plots slight right skew and no strong outliers. The QQ plot deviation from normality as expected. The distribution fits Poisson characteristic well, indicating right skewedness and discrete nature. Next is exponential distribution. The histogram with KDE is right skewed tail decay. For the PDF curve, aligns well with histogram, especially for small values. The box plot is right skewed, median left of center with no outliers. The QQ plot deviates from normal expected for exponential data. And for the conclusion, data follow exponential distribution, strong skewness, and non-normality are consistent with the model. Lastly, the uniform distribution. Graphical indicators or histogram with KDE even data spread flat KDE. The PDF curve flatline confirms constant probability. The box plot symmetric centered with no outliers. And the QQ plot significant deviation from normal expected. For conclusion, data matches the uniform distribution, even spread confirmed not normal as expected. So that's all for the simulation result, and we'll be discussing for the next reporter for Miss Hannah Ropeta.
In this part, we're going to compare between the statistical methods we use in our solution and traditional theoretical approaches. So for parameter estimation, both our solution and for the theoretical stat used maximum likelihood estimation or MLE. So they are well aligned. So next, when testing continuous data, our solution uses the KS test. However, this test is ideally assumes known parameters which we estimate from the data. So it is only partially aligned. And for the discrete data set, the system correctly uses the chi-square test. So it is matching the standard statistical practice. And in terms of choosing the best fitting distribution, we use the max p values for ranking, which works for exploration but isn't as rigorous as criteria like AIC or BIC used in theoretical modeling. Lastly, we incorporated multiple visualizations such as KDE, PDF, and QQ plots, which are standard tools in both practical and theoretical analysis.
For our conclusion, the main problem we addressed was how to correctly identify the type of distribution a random dataset follows. To solve this, we use a Python program that takes user input, parses it into data, and evaluates it against several possible distributions. Using statistical tests, we started by drafting a pseudocode and flowchart to clearly map out each step from parsing input, evaluating distributions, calculating p-values, and choosing the best fit distribution for the dataset provided. So the actual code then automated this process efficiently. During the simulation, we analyzed key statistical properties like the mean, standard deviation, and skewness of the data. We then compared those to the expected values of each theoretical distribution. Through this activity, our group learned that determining the best fitting probability distribution isn't just about guessing based on the shape of the type of the distribution, but it also involves a full process of input validation, statistical thinking, and comparison. We also learned that the application of statistical thinking in the structured way. We saw how math and programming can work hand in hand to interpret data more accurately. In addition, it also helped us appreciate how powerful simulations are for testing assumptions and building confidence in our conclusions. That's all for our presentation. Thank you and have a nice day.